welcome to CS Teaching Talks, where research meets reality. I'm your host, Dr. Emily Tomford, and when I'm not reading or discussing research, you can find me teaching computer science to pre-service teachers at Reach University. Today's paper is entitled Abstraction in Action, K-5 Teachers' Use of Levels of Abstraction, particularly the design level, in teaching programming. It's by Jane Waite, Paul Curzon, William Marsh, Sue Sentance, and Alex Hadwen-Bennett, and it's published in 2018 in the International Journal of Computer Science Education in Schools. I'm delighted to welcome this week's guests. Thank you all for being here for the CS Ed discussion group. We're going to go around and introduce ourselves. So my name's Emily Tomford. I'm a professor of computer sciences at Reach University. My pronouns are she, her.
I'm Jane Waite. I work at the Raspberry Pi Foundation and I'm doing my PhD as part of Queen Mary University of London, and I identify as she, her.
I'm Jeff Sear. I'm a K-4 technology and computer science teacher at two rural elementary schools in central Maine in the United States. I use he, him pronouns.
Hi, I'm Shujal Hassan. I am founder of an edtech startup in Pakistan. My pronouns are he, him.
Hi, I'm Elizabeth Bacon. I work at Curzon, and my pronouns are she or they.
So today's paper is entitled Abstraction in Action, K-5 Teachers' Uses of Levels of Abstraction, particularly the design level, in teaching programming. And this is a 2018 article published in the International Journal of Computer Science Education in Schools. And we are privileged today to be joined by one of the authors. Could you give us like a high-level summary of what you set out to do in the paper and maybe what your core conclusions were?
So this was my first study in my PhD. And because I had been a primary school teacher and had worked in developing resources, I felt there was a gap in what we knew or what we'd evidenced in the area of particularly around abstraction. And I started off with this really kind of grand idea. I would research abstraction in general, but it became very apparent very quickly that I had to be more specific. And there's some research done by Mikhail Armoni in Israel, which builds on work that's being done with older learners. And they have this thing called, Mikhail, she created this, the levels of abstraction, which includes, it's a way of looking at an algorithm really, but at different, she calls them levels. And that builds on other people's work as well. And so I was interested in this as a way to look at abstraction, and I wanted to see what that looked like in practice. So I found 5 local teachers, 2 of whom were very experienced teachers, 2 were not very experienced at all in terms of teaching computing, and 1 who's in between. And I created a way to get them to talk about how they taught programming. But what I wanted to understand was what they thought an algorithm was and what they thought design was, because that's a form of abstraction in terms of a representation of the program as it kind of goes, the activity occurs. And so I kind of devised this way of, I had these little pictures that described or that represented these levels, which are effectively the requirements of the task, the design that includes the algorithm, kind of code, and then the code executing and running. And I had all these activities that teachers did. They had to order them and sort them, and there were lots of different projects, and they just talked about their kind of what they thought an algorithm was, what they thought design was, and what they kind of how it all fitted together. And what I really revealed was a huge amount of confusion of what an algorithm was, complete confusion, and that was both within teachers who are less experienced and more experienced. But yeah, so it's all about looking really at design as one form of abstraction, and specifically at what an algorithm is in relationship to design.
If I could just ask a follow-up question of Jane, just can you clarify what you mean by design? Like, what are we looking at designing in this situation?
It's a really good question. So if they're students who are from the age of, so they're kind of 5-year-olds through to 11-year-olds, so K-5, and they're doing programming activities, And those programming activities, they might be getting a little bot, like a little programmable device to run around on a mat. And so then we're talking about the design being potentially, and this is kind of moving you all the way on to my later studies, but it's maybe thinking that it's might be in the format of they're just thinking of it. They're just thinking in their head. They're planning ahead the steps. So that's the design. Or it might be that they're going to note it down on a piece of paper, or they're going to act it out. So there are different formats that you can represent a design in. And what that design looks like, there are components, but this is going way beyond this paper because this is like 8 years on. There are different kind of parts, components to that design. So
I was just kind of wondering, and I kind of had a sense, but basically that there's a programming task or there's a robotics task, and design is sort of the planning, either explicit or kind of internally about how to approach the problem that they're trying to solve.
If you recall that I kind of built on Michaela Armani's work, and she had these levels of abstraction that she called execution, program. She had it called, the third level was called object, and then problem, but it's the other way around how I formulated it, because I then compared it to Quentin Kutz's work, where they called it the abstraction transition taxonomy, and then there's some other work. But in the end, the kind of what I was looking at with primary school teachers was there's the problem. In fact, they didn't want to call the task the problem. They said, no, it's not a problem, it's just a task, because problem sounds like they've done something wrong. And you talk about that in English, and it's what's needed. Then you have this design, which people usually use kind of CS speak to talk about. It's what you should do. Then you've got the actual code that's been implemented, and then you've got the code that is executing and running on the machine. And again, I found they didn't like the word execution, so we went for running the code.
I definitely notice with my kids the first two levels can be a real challenge. And part of it is that they're young kids and they don't want to do any planning. They just want to, play and do the things, and that's understandable. But certainly, I've noticed that they do struggle with not just kind of designing a solution, but even sort of identifying what the problem is. And so I can definitely see how you progress down each step as kind of another further level of abstraction away from the previous. So yeah, this does make a lot of sense. And I definitely see how the kids can struggle or succeed at each portion of it.
The problem level, or later the task level, is that considered the most abstract?
I think that's a good question, because to be honest, I've kind of moved away from my concern too much around abstraction now. I think very much around design and algorithms. So I think everything's an abstraction in a sense. I think that's the problem with that word. It's just a different view of the same thing with different levels of detail, different kind of formats and representations. And I think what's interesting as well, going back to what Jeff said, that the idea of the levels is that you kind of will go to each level lots of times. And the big deal is about supporting children to transition between the levels. Again, going back to the work that Michaela Armani did, she had a PhD student. I can't remember his first name, but his second name is Stata. Anyway, they did research with older learners. And what they found was that young people made more progress if A, they could identify the level they were working at, and B, they could understand, they're starting to understand how to transition. And kind of this idea of levels of abstraction has become really quite popular in some of our UK resources now. And it's something that has featured throughout the rest of my research. So yeah, it's not that it's linear, it's more that it's, you might come in and start with the code, an activity might start with the program. It might actually start with a use, which actually is at running the code. And then you might kind of move through the levels in all sorts of different order. But I think that, again, what Jeff was saying about children maybe being reticent to design. My second paper was a survey of over 200 teachers to draw out what the difficulties with design were. And one of them was kids don't want to do it. And so, you know, and then there's all sorts of other kind of things. But teachers are overcoming that by using techniques that they use in other subjects. And that's something as well that featured here, was the kind of parallels with teaching planning in writing.
Well, I was going to say there were a couple things that I really appreciated about what this paper brought, and it was long, like it brought a lot of stuff to the table. But one is really making those parallels between especially literacy and the pedagogies we get from that, because I feel like there's a lot of stuff that we were really trying to pull out of math and to a certain extent the sciences that didn't actually speak to what a lot of kids were struggling with, which are the decomposition of the problem. And really, we focus so much on the syntax and learning these algorithmic constructs. And I think especially as it moved down into the lower levels, we were seeing there were skills that we just kind of like thought kids would have. And I think the classic example that we saw is like understanding that a house is a triangle on top of a square. And that is not obvious. You know, it's just something that we've learned over time. And so we think it's obvious, but it's not. So those skills, and I think that bringing in especially the stuff from ELA of sort of how do we take an idea that is maybe amorphous in our heads, and what are the different ways that we can use to make it concrete. I really appreciated that. And although I have to say, I agree that I was not as keen to think about it as like levels of abstraction in the same way. What I did appreciate is that this isn't about doing a step and completing a step and now doing the other step. So that's like being able to say, okay, I have this comic that I made of my Scratch thing, and like this panel goes with this code, or like this picture goes with this sprite. So being able to make those connections between those two sort of ways that you're communicating about your idea. So it's like we can communicate our idea through a story, we can communicate through a picture, we can communicate through code, all of these different forms of communication. And where we found those parallels, I found that was really good, because then we can say, okay, so maybe you like this code thing that you did in the code, so go back and change your picture, or, you know, like this, or maybe, you know, you're going to think about it in a little bit different way. But and I know, Jane, I said this like years back when I was at the PD that you ran, like I felt like kids did like the design aspect. But it was because, you know, they were excited about their story. You know, they want to tell you about their idea. Maybe if you say like, now we're going to plan, it's kind of like a visceral reaction to that, but they're excited to tell you about their program. Maybe if they can draw a picture of it, that, you know, they're keen to do that. But I think there is something about like, when I was a kid, when my teachers like write an outline for your essay, and I'm like, bleh. And now I always want to write my outline first, because it's just like makes it easier. So I think that, you know, pulling in those things for English was super helpful for being able to operate around all those things.
When kids don't want to design, is it because it's just too easy? You know, do they kind of need to be challenged a bit more, or do they not want to design because it's too hard? So again, it's like, how do we get the in between? But again, teachers, I think, in other subjects, they kind of, and one of the things that some of them, again, taking it further forward in my research, is that teachers, they model, they kind of exemplify, they help learners realize how useful these things can be, but they don't wed them to it, so that when it's no longer useful, it kind of gets dropped. However, at the end, there are opportunities to go back. So, you know, the teachers were using design in really cool ways to help with differentiation, assessment, to know what's doable, all sorts of different ways. But I think that there is this initial kind of tendency that we have to start by coding, but maybe that's because we don't know what's doable. So you need to start with the use, before you got to the modify and create?
Yes, definitely. A lot of it is resonating with me because we only recently thought that we should have some sort of a design phase in our level 2 program at the end of it. And we sort of tried to provide some form of scaffolding that what backdrops you want to create, what sprites you want to incorporate, what will be the program for each of those sprites, and not just we didn't use the word program, what actions each of the sprite is going to perform. And now I'm looking at it that what is needed, what it should do, how it is done. And I also sort of resonate with what almost everybody over here has said, that kids just don't want to go through the design phase. And we had anticipated that they would take 2 weeks to cover that process and get a project proposal and then get it approved and then start working on the project. But it has taken about 4 weeks, and this is our first trial that we have tried to incorporate this. And I do believe that if we would be able to maybe show an example of how this process would be useful to them, then they would see the value in it as well. Because, and it's just like you've said that if they would if it is in their head and they want to just start building it because that's more fascinating to them, then why would they actually go through the design process unless it would be helpful for them in any way? So we definitely need to do something regarding that.
That again resonates with what teachers said. One of the quotes is really brilliant, was something about, well, like when they get stuck, I say to them, well, what do you want to do? And they say, I don't know. And I say, well, I can't see inside your head. And so I think, again, there's kind of, I completely agree with you. There's this thing of it needs to be useful. But I think as educators, we need to have rehearsed and practiced ourselves and have examples and models. And maybe just like we do use, modify, create with the code, we need to do use, modify, create with the designs. So it's just part and parcel of what we do. And so maybe we give them a design to begin with, and then they build off it, or we give them a design and they amend it. And if in English, in England, we have something called imitate, innovate, invent. And so we kind of go through that same process, but with the planning as well as the actual the implementation. And there's the same thing if you think about in maths as well, because we have approaches that we use in maths, and we help children to learn to plan ahead, to go, I'm going to use the bus stop method, or I'm going to use this method, or what method they're going to use.
There's this also relates to a different problem as well, that when we tell them that they have to come up with a final project presentation, something to be created completely by themselves, they can take help from other people's programs or maybe from YouTube tutorials, but then they can actually replicate the entire code from a YouTube tutorial without having to understand it. So we thought that we would add a next feature into this, that whatever they would submit as a next step, we would discuss it with them that you have to add a certain new feature into that project, something that would be outside the scope of that tutorial that they've probably looked at. So that's how maybe this like design process could also be supplemented, that you could say, as you've said, Kay, add something to it.
I do want to go back to something you alluded to earlier, which was I love that the study was, this initial one was around 5 teachers and really looking at their use of vocabulary, what they called things, how they ordered things, what importance they gave to everything. And one of the concepts that came out of that was their general disagreement on the definition of algorithm. I thought it might be fun to dig into that a bit. Let's put it to Jeff first. So do you and the people you work with, does your community have an agreed upon definition of algorithm? Or is there confusion within yours?
I don't know. I'm kind of on an island where I work. I think there are other teachers in the district, but we don't get together super often, so we don't have a lot of opportunities to talk about it. So I kind of use the definition that I share with the kindergarten kids, that hopefully is not too complicated, which is just a list of steps. And that's kind of the one that I go with it in simplest form. But I can't say I've had a lot of conversations with other colleagues about the meaning of algorithms. Sorry.
I think that's very indicative. Like, just looking at these 5 teachers, knowing that they don't agree about the vocabulary, and just hearing from you, Jeff, that you're teaching in basically in isolation, right? It's the community and the crosstalk that allows us to agree on common definitions. And if we don't have that, right, we really can't expect, a shared definition.
You could argue, in a very purist sense, that they're all forms of an algorithm, whether it's the code or the code running itself. But that's kind of far more about abstraction and those kind of things. But for the students, there's a design, and we're kind of associating with the design this idea of an abstraction of the implemented code. But what, like I say, for an animation, what does that look like? Or for a quiz, what does it look like? Or for I don't know what else it could be, like a drawing program, what does it look like? And I think that was what was interesting, was it wasn't really 100% clear in everybody's minds.
I think I would be one of the pedantic people who not only could argue that, but would, that an algorithm is abstract enough that because it's at a higher level of abstraction, in order to interact with it, you do have to express it in some way. And whether you're expressing it in like normal English terms, or whether you're expressing it through a particular code language, like it's the instructions themselves and not the particular like method of communication. So I would argue that you could express an algorithm as as a picture. You could express it as English. You could express it as code. Now, obviously, code is the easiest way to express an algorithm to allow a computer to execute it. And English, there are other ways that would be easier to allow a human to understand what's going on. So that would be sort of how I would think about algorithms. But I think that to understand that, like, I think it is important for kids to understand that you can express your idea in a way that's not code. And that it's important to be able to do that, and also to kind of understand that code is a form of communication, and that we're, when we're doing stuff, we're either communicating so that a computer can execute it, or communicating so that a person can understand our idea.
This problem that we have with algorithms, and it is a problem, it's fine for those who are more experienced programming teachers to grapple with and worry about. But if you're a newbie to it, don't worry about the problems with algorithms. Just act it out or draw it. Don't worry about whether it is or is not really an algorithm, but maybe at least distinguish between the algorithm being something that's at the design level and the code, which is an implementation of it. And then when it runs, the execution. So these levels of abstraction.
There was a part of the paper which we alluded to earlier around using different design types for different subjects. So I'm looking specifically at section 5.5. Integration is a hot button topic here. Everyone loves when you can say integration. And this kind of points to bringing practices from planning and design from other subjects into computer science. How can K-5 teachers make that actionable?
Teachers, you're doing it already. You kind of know in your head that there's all these different genre of activity that you're going to be doing, just as there are genre of writing, or there's different types of math problems, and that you're going to have to somehow cycle through them. So there's something there about, first of all, having an understanding of all the different opportunities, all the different project types, which I call genre. And similarly, there are genre in other subjects. For example, storyboards are very popular in literacy, but concept maps tend to be more popular in science. So there are different planning and design kind of formats in different subjects, which may then lend themselves to computer science. But what was absolutely clear was teachers understood the affordance of these different formats, and they were making the links intuitively, but they'd never spoken about them before. And it was almost like I asked them these questions, he went, oh, yeah, that's that. So all I feel like I've done is I've just asked some questions and found some common things that teachers are doing, and we've just made some labels for them.
In my school district, we're trying to figure out like what integrated computer science and computational thinking looks like. We kind of acknowledge to some extent that like a lot of this is happening already, and so it's really like it's almost like it's more about the vocabulary. It's just like making sure there's consistent vocabulary, and also maybe even just like making sure there's almost like consistent modeling. I want what I'm teaching them to be useful when they go back to their classroom teacher. And I want what they're learning in their classroom to be useful when they come to me. And so I think we're trying to figure out what those connections look like, in terms of vocabulary, in terms of like what we're doing, like the output of whatever activities, but also like trying to figure out how to overcome some of the barriers to this, like particularly just like the lack of professional time to actually connect with teachers and talk about these things. Because I've been involved in a couple of different projects with classroom teachers, and having the time to talk with them as part of that has led to a lot of different things and a lot of different understandings. It's like, how do we actually find that time when there are so many demands on it?
Jeff, I have no clue how we're going to do that apart from magic.
Well, and I think too, just to build on that too, thinking about, in my district, and I don't necessarily know how it is in other places, but at least here in Maine, where most of our districts are very small. I work in a district of about 2,000 kids, and that's like a medium to medium large size district. And so thinking about like the fact that we have a dedicated like computer science and technology class at the elementary level, like with teachers, like that's our content. Like we're immersing ourselves in these things. And, so we have kind of experts to talk with teachers about this. And I would say that is definitely not the norm. So then you have this other piece of like, now you've got teachers who are not familiar with this content, who don't necessarily have that resource in the building. And now we're asking them to figure it out for themselves, which is like a whole other layer of like, how do we overcome that?
What are you taking away? Right? What are the implications for K-5 teaching?
I think that until we really have an understanding of what we want them to learn, like what do we want them to learn about algorithms? If we don't agree on what they are, then how are we expecting the kids to have any coherent educational experience? But I think that, things like this and, the paper, the discussions, the work with teachers are an important part of us kind of getting there. But the other thing that I'm really pulling out of this, and also the things that, Jane brought up about just working with teachers, is we have so much expertise from teachers, the pedagogical expertise. There's so much transfer. Even, we talk about discipline-specific pedagogy, but then it transfers over. So how are we as a community really leveraging that and giving space for teachers to both kind of like get that content knowledge, but also while really respecting all of the expertise that they're bringing to the table? And I think that having these starting points where we can collaborate and kind of like have these frameworks and maybe disagree on what we call them, but kind of come together at the end is super important. But I just feel like it's a long road. Like it's been 2018. I feel like we have come a long way, in a lot of ways, but it's also, I think of how far we have to go at the same time. So that's kind of top of mind for me.
What do we prioritize? Do we prioritize teaching algorithms at an early stage, or programming concepts? Because as you also mentioned, that we're limited by the time. And when we bring in interdisciplinary things, then we have to cover multiple objectives in the same time slot as well. So that's also a challenge. So these are probably the two things that I'll be looking up after this.
I appreciate all the resources that Jane has shared. I mean, this is an absolute treasure trove, and I'm looking forward to diving in. And I guess the takeaway piece is I've got a lot more thinking to do about design. and figuring out how I want to implement that. Because definitely like that part of it, I would say, is something that I'm struggling to actually do with my kids to support them in the way that they need to be supported. So I definitely want to take more time diving into that.
Jane, I'd like to give you the last word. If there's anything that you want K-5 teachers to, even if they haven't read the paper, even based on your work that's more modern than this, like what is your core message for them around design?
So I'm going to link it actually to teaching. Most K-5 teachers are generalists, and they spend more time teaching literacy and reading and writing than they do computing. And when I asked teachers how important and useful was, planning is in writing, and they said it's essential. And I said, do you ever not plan? They said, you must be mad. Of course we do. We always plan, even if it's just a quick sketch, but we have to think ahead. Who are the characters? What are they going to do? What's the beginning? What's the end? And I said, well, what about this idea of planning, designing, computing? And they went, yeah, it's just as important. And I said, but do you do it? And they said, no. And there's this kind of disconnect and I said, why is planning important in writing? So it's the kids know what they're doing. They can tick off where they're up to, so I can assess, so that we can differentiate. The kids know where they're. And I said, would that be handy in if you were doing computing? They went, yes. Why don't we do it? Well, because the kids don't want to do it. And you go, do the kids not want to do planning in literacy? And they go, yeah, to begin with, they don't. But then they realize it's a good idea. So I suppose that's the thing is, if you teach writing, just use the same tricks. Model it, make it simple, reuse the same formats, those kind of things. Maybe, but we have to do the research.
Well said, and thank you. That was so cool to have all these people and to be joined by the author. It's always a delight. Well, thank you all for listening to this episode of CS Teaching Talks. We had a rousing discussion of the paper Abstraction in Action, K-5 Teachers' Uses of Levels of Abstraction, particularly the design level, in teaching programming, by Jane Waite, Paul Curzon, William Marsh, Sue Sentance, and Alex Hadwen-Bennett. If you would like to join us in any future discussions, you are welcome to. We meet on Tuesday and Friday evenings or afternoons, depending on your time zone, and no one needs to prepare or read the paper ahead of time. Just show up and have a conversation with us. And we'd love to hear from you. Please use our email address, podcast@csedresearch.org, to send us any questions or thoughts or papers you think might be interesting for us to read. The CS Teaching Talks podcast is presented by csedresearch.org and Reach University. Funding has been provided by the Association of Computing Machinery Special Interest Group for Computer Science Education and Amazon Future Engineer. See you all next time.